Afternoon, everybody. Today we are very happy to have Professor Vanarelli from the United States Department of Energy, Office of Environmental Management, the water isolation pilot plant in the Carlsbad field office. And we have a professor who is a multidisciplinary engineer when it comes to geology, civil engineering, environmental law. And he acquired his BSc in Rutgers University, and for his advanced degrees, that's a master's PhD, he acquired them right here in Colorado School of Mines in mining and earth systems engineering. He's a professional engineer. He's also a professional geologist certified in several states. And he's also served as the ABET engineer and an expert conducting accreditation visits internationally. So without saying much, shall we welcome Professor Vanarelli with a round of applause.
Well, thank you all. Thank you all very much. Thank you for coming today. I'm experiencing a little bit of deja vu. This is actually where I used to teach rock mechanics in this particular room. And actually, looking around, not that much has changed. So in any event, it's been quite a while too. But in any event, that's fine. So yes, I'm here to give you a short presentation on what's described as the WIPP facility. This is the U.S. Department of Energy's deep geological underground repository for transuranic waste materials in Carlsbad, New Mexico. Let me describe a little bit of history here. Actually, the facility actually began investigating this particular site geologically, the subsurface conditions back in the early 1970s, actually. And they pretty extensively investigated it starting at the beginning in 1975. The shafts that began the construction of the mine are the waste shaft, the exhaust shaft, the air intake shaft, and the salt and the did I cover it all? No, air intakes, yeah. So in any event, there's four shafts basically that supply air and allow it for the removal of air, and also. Basically, this facility actually started in 1983. The first shafts went in and the waste shafts. Those shafts actually were the waste shafts, and those other shafts were installed over a period of time. And the facility became operational in 1999. That's when we accepted our first transuranic waste materials. So you might ask yourself the question, so we've been operational since then. So we just celebrated actually our 25th anniversary. And actually we were supposed to be completing our deposition or emplacement of waste this year. Unfortunately, we have not been successful in doing that. We've emplaced about a little over half of that material, which is 6.2 million cubic feet of waste materials. That amount of material probably at some time will be expanded upon, but right now we're in the process of emplacing that waste, and it's anticipated that this facility will probably be operational for as much as another 50 years, if not longer, up to 2075, even up to 2085. So what is WIPP? WIPP is what we call WIPP is the Waste Isolation Pilot Plant. It's kind of the name is kind of a bit of a misnomer. It's probably a bit of an antiquated name, actually. It's America's first deep geological repository for permanent disposal of defense-generated transuranic radioactive waste materials. That's generated from research and the production of nuclear weapons. WIPP itself is actually it's a salt mine, basically. It's functionally a salt mine, so we're not mining salt per se. We're simply creating open space so that we can emplace radioactive waste in the underground. Okay, this salt formation, actually, the geology here is actually quite stable. We're actually installing this waste in a salt formation that's about 2,000 feet thick and very extensive, actually. If you look at this area, this was originally part of the Permian Basin. It's a depositional sea that occurred about 250 million years ago, well, 295 to 250 million years ago. So it's pretty extensive. It's in this area, this vicinity. It's in southeastern New Mexico. And so it's like this facility was developed to and placed this waste over a period of time so that it won't move. It's basically stable. The area is very stable. It's a desert type of environment. There's not much water there as a result of the fact that it's a desert. We only have a little bit amount. We have one or two minor sources of water for this that impact our mine, but very little more in general. Salt was selected as the medium for placing this waste because it is plastic. It has a plastic characteristic that it basically yields to stress by deforming, but deforming very slowly. We refer to this as creep. This creep type of characteristic actually allows the waste to be ultimately encapsulated, entombed into the rock formation. So again, we're down at depth of 2,150 feet below the ground surface. The salt formation itself starts around, I'd say, about 1,000 feet below the ground surface. And we are at the center. The repository itself is in the center of the formation. Okay, so the formation that we're in is it's called referred to as the Salado Formation. It's a massive halite formation, so it's very extensive. It's I said it's a part of it was created as part of an evaporative sea, referred to as the Permian Sea, which formed the Permian Basin. Again, we're about 2,150 feet below the ground surface. Okay. Transuranic waste. You might ask yourself, what is transuranic waste? It's basically things that have been exposed to radiation and have retained some measure of radiation. Those things such as clothes, gloves, tools, any type of debris. That's actually what transuranic waste is. It's a relatively low level concentration of radioactive waste. We do not import any kind of uranium or plutonium into the underground here. That is reserved for Yucca Mountain, which has actually never been opened up. At least it hasn't opened up yet. But in any event, what we place here is relatively low-level radioactive waste materials. So we've been producing transuranic waste for approximately, I'd say, since the 1940s, since we actually generated nuclear weapons. And so this is basically how that true waste actually is embedded in the soil formation. So geologically, the cross section of this site is actually, these are exclusively sedimentary deposits. So what we see in this particular above and below the soil formation is sandstone, siltstone, dolomite, mudstones. Those are the types of formations that we typically observe in this formation. We do have one small area, a small zone that produces its water bearing. It's permeable. It's about 30 feet thick. It's called the Calibre Formation. It's a dolomite. It's fractured dolomite, in which water is produced out of that site, out of that formation. And it does yield we have to address some issues with our shafts, actually. The shafts actually end up producing a small amount of water. They're concrete lined, the shafts, down to the salt formation. Unfortunately, that still means that there's a small amount of water that still leaches down into the underground, into the bottom of the shafts. And we collect that water and we remove it to the surface. And we do everything we can to seal that off from leaking. And we actually have proposed several remediation techniques to kind of remediate that situation, mitigate that situation from occurring. Okay, so this is a close-up shot of what the excavation looks like in the repository. We try to align the excavation itself with clay seams that are above the formation, above the excavation, and also there's other seams of halite and hydrite and other constituent layers. We want to get as close to that clay seam because we don't want it delaminating from the above overburden materials. So we typically we'll do some additional reinforcement. I haven't said it yet, I guess, that our design for our mine, these are sedimentary rock deposits. Our mine design is a room and pillar design. For those of you who have taken rock mechanics so far, you know what I'm talking about, a room and pillar design. So we basically have a room that we develop, but there's support, there's materials that are left in place to support the overburden material. Those are our pillars. You'll get a better image of that in a moment. So we have forces at depth that we are contending with, both vertical forces and horizontal forces. Again, we try to align our excavation as close as we can to the overlying clay seam. In our particular excavation, we actually changed the elevation of our excavation at one point or another to be closer to that clay seam so that we could anchor our rock bolts above the clay seam itself. I did show you some images before. I guess the product of why we're trying to avoid that, we end up generating some low angle fractures if we don't get really close to that clay seam where we can secure the back, that is the roof. So this is just a depiction of us anchoring the rock bolts up against the back. Okay, so our rooms are basically, as I mentioned before, what we've done is in the process of drilling our shafts, we've constructed drifts and drifts that align in with our crosscuts and events that we actually create several panels. The panels are actually where our rooms are constructed, and that's where we place our waste. So the size of the rooms are generally of a size of 33 feet wide, 300 feet long, and 13 feet high. So to date, actually, we've created 8 full panels. Some of those panels are actually completely have a place radioactive transuranic waste materials, and they're closed off at this time. We're currently working in panel number 8, which is this one that's outlined in green here. But I think we're in room 5 right now with the placement of transuranic waste. So this has been closed. This has been sealed off right now. So over here, actually, and this is like, these are the 4 shafts, our waste shaft, our exhaust shaft, our salt, this is our exhaust shaft, salt shaft, and air intake shaft. And over here is our new shaft, actually, we just completed this. This is the utility shaft. And we're gonna do some additional airflow into the extended part of the west main of our mine. So this is the alignment. This is the north-south alignment. This is going west and east. So we're expanding out this way. Okay, we're going to construct new panels. This will be panel 11, 12, up to 9 additional panels in this area along the west main. So as I mentioned before, what's transuranic waste? It's clothing, tools and rags and debris of any sort that's been contaminated with man-made radioactive elements that are heavier than uranium. So we have 2 types of transuranic waste that we place in the mine. One is called contact handled waste. It's primarily emits alpha radiation. Alpha radiation is it's pretty fairly low level radiation. It can't penetrate your skin, so which is a good thing. So we basically place that waste. 96% of our waste is actually contact handled waste. It's basically of a very low level. Alpha particles are basically relatively harmless unless you ingest them. That's why you hear of incidences with, I guess, with Russia, like poisoning somebody's coffee with plutonium. And plutonium only emits alpha particles. But if you ingest it, it really can kill you. And so you don't want to ingest it ever. So that's one of our types of waste, contact handled waste. We also have what we call remote handled waste. That is a slightly higher level of radiations emitted from this remote handled waste. And only 4% of our waste material is actually remote handled waste. So this particular instrument, this is a boring machine, and we're basically boring into our pillars, actually. That's where we put our remote handled waste. The contact handled waste, again, is basically stored in the rooms. It's in place in the rooms. Okay, this is the footprint, which you have kind of already shown you already. This area over here, on the left side of the map, is the area where we do our research work. We have Lano and Sandia conduct research currently at our facility. Okay. I already talked about this a little bit. So this is how we place our waste. We basically set these 55-gallon drums, which is what they're overpacked a bit. 55-gallon drums contain our transuranic waste. On top of the 55-gallon drums, we can place mag oxide, which absorbs any moisture that might come off of the containers if they're breached when they're being entombed in the salt. So this is just show the picture of rock bolting machine. So we've been operational for 25 years now. So in 2014, unfortunately, we had two events occur. One was a fire in the underground. As you all know, nobody wants a fire in the underground. You have a confined space, you have limited amounts of air, and fires love air. They love oxygen. So that occurred, and right after that, a week or two later, actually, we had another event occur with one of our containers actually was breached, and released some radioactivity, and that shut down our facility, our mining operations, for a period of 9 to 10 months. So it was pretty significant. We weren't able to get in the underground for that period of time. Therefore, we weren't able to do any additional reinforcement with rock bolting and wire meshing. So what the effect of that was this back, the roof here, began to belly out. And so we needed to address that. And what we've done in the past historically is we've rock bolted the heck out of the thing, and which is fine to a point. Although at some point you end up rubblizing the back. And that's pretty bit problematic how much longer you can continue to do that for. So we have some other ground support systems we've kind of evaluated to see how far we can extend out the life of the mine. I tell you now, right now we haven't emplaced all the waste that we were supposed to emplace in the underground as of yet. We have about half that amount still in place, and so it's been projected out that we're going to be in operations for another 30 to 50 years and perhaps longer. So again, up to 20, as long as maybe 2075, 2085. But I can't predict the future, so I don't know exactly how long the facility will operate, but that's what's been projected out right now. Okay, those are some of the canisters in the mine. But this is actually the canister, the 55-gallon drum that was breached actually, and caused the radiological release, which led to the fact that we weren't able to get into the mine for 9 to 10 months, and then actually even after that we had limited work. We were restricted in what we could do in the mine for another 2 years. So I talked about the back bellowing out the way it was. There was this concave shape that it formed. We needed to take a look at other ground support systems. And so it was proposed back in 2009 that we take a look at yielding arches as for supporting the roof, and we did that. Actually, myself with a small team of other people from Simco, which is the contractor, which is a subsidiary of Bechtel, and also a subcontractor referred to as known as Genmar. I'm sure you've heard that name before. Actually went out to sites in Europe actually to look at the steel manufacturing facility for these yielding steel arches, and also we also went out to two mines. One was a salt mine, another one was a coal mine. I'll show you some pictures of that in a minute. But anyways, this was the proposed alternative to what we have been doing. The fact that we had rubblized the back in certain sections of the mine. Now, of course, we don't need to keep the entire mine open. We want it to creep. We want it to encapsulate, enclose, and entomb the waste material. So in the panels themselves, those will be allowed to encapsulate the waste material. But in the drifts and in the crosscuts, the drifts that we use for transportation routes, those things need to be kept open for an extended period of time for personnel, for transportation, for personnel, for equipment, for removal of waste, and placement of waste, and also removal of salt. So this is what the steel arches look like. There's basically two frames, basically steel sets that are aligned with one another. They slide over one another, and they're clamps wrapped around those two steel beams, and they slide over. They basically yield over time through the deformation, the strain that's occurring in the rock formation above, in the back, and the ribs. We also have steel frames at the bottom, at the base of the yielding arches to deal with floor heave. Okay, so these yielding arches are in the form of an arch. Typically, that's how they're constructed. If you notice, if you recall, our excavation is in the form of a rectangle. So we have a little bit of a space issue. So we have to use some backfill material. What they propose, Genmar has proposed using J-Seal as a backfill. So ultimately, we don't want to do that for too long a period of time, and placing concrete or concrete-like material in the underground isn't advantageous because we don't want to impose or place any additional water. Concrete has water in it. So I mentioned those low angle fractures, and here's an example actually. So very nicely that low angle fracture. You're not near enough or not reinforced against those clay seams. Okay, the bottom is a road header. What's been proposed is that we can re-excavate the rectangular excavation in the form of an arch, such that we don't have to use any backfill at all. Okay, so we went to this steel mill fabrication facility, and we visited two mines. One was the salt mines. It's the Valeshka salt mine, actually, which is east of Krakow. That's a very, very old mine, actually, which just closed down in 2007 to become a tourist mine. The mine actually had been operational for about 800 years. So, and we also visited the Sola coal mine, which is kind of Poland, which is just due west of Krakow. So the steel mine was the fabrication. We looked at a number of designs for the yielding arches. How do we prevent floor heave? How do we structure this thing in such a way that it won't it'll absorb as much of the excavation or deformation that occurs in the excavation. So this is some photographs of the steel manufacturing plant. And they just show us some testing. They did testing of the steel beams. To show us the compressive strength of the steel beams, and also the clamps. So this is the group that I was with. Again, Genmore representatives, Simco representatives, and the managers of this steel manufacturing facility. So we subsequently, we went to southern Poland and visited the Walecka salt mine, in which we observed the yielding arches in the underground there. This particular mine is only about 400 some odd feet below the ground surface. We're not particularly, not at the same level that our mine is at, but nevertheless, these yielding arches have been utilized there for over 30 years. So, and they use, for their backfill material, they use slats of concrete. So the utilities and what have you are hung along the ribs. So again, this particular site is about this drift is actually the tourist part of the mine. We did visit the tourist part of the mine, but we also visit, this is not accessible to tourists, actually, this section of the mine, but it doesn't have any issues or support issues. They also use, on occasion, they use wood as a backfill type of material. At least historically, that's what they did. So for the Venezuela coal mine, actually, this mine is close to 2,000 feet below the ground surface. So it's experienced the same level of stresses and deformation that we are used to, actually, in our facility, in our mine. This is a coal mine. It's a sedimentary mine. They do have issues with groundwater at this mine, which is not that unusual, and they pump that water out. They have actually quite a bit of water that flows into the mine, and they basically manage it. Okay, so this mine uses yielding arches very extensively. The drifts are quite long. The width of the drifts is actually much wider, where they utilize these yielding arches. You can see here. And some of these drifts are actually at least 30 years old, and actually the oldest one is actually, which we observed, was 50 years old. So this is a location where two drifts actually, which utilize yielding arches, come together, intersect, and even at the intersection, they utilize the yielding arches as well. Okay, as I mentioned before, some of the connectors. You see some of these connections, they have to use a certain, they're going to have to redesign this for us, for our purposes as well. So there were a number of proposals, a number of models that were generated, that we might, some ideas that we might be able to use for our particular mine. Okay. Let's see. So this is a group again where we were at the coal mine here, and so we had to utilize. We had to get on all this personal protective equipment to go into the underground mine there. So and we had to wear boots just because of all the water that we observed. Okay, that's my presentation, and I'm open to questions.
Very much.
Sure.
Wonderful presentation. Time for questions, comments. Anything on your mind?
Start off here.
Sure, Jamal.
For your remote handle, it says that you're drilling into the pillars, right?
Yep.
Are these pillars between your rooms in a panel or separate pillars or into barrier pillars?
Yeah, they're actually into the rooms, actually. Yeah. So actually, I proposed to them that I think maybe perhaps that needs to be evaluated. At least I think they're pretty widely separated apart, though, these boreholes that they're before they install this waste material. So I'm pretty certain we have some very experienced miners that have been there for 30 plus years, actually, who have evaluated this. Right now, we're not in placing any remote handled waste at this moment because of the events of 2014. We've concentrated on contact handled waste almost exclusively. But there are plans to start that portion up again. And I expect it will happen soon, actually. The yielding arches, actually, originally we proposed to install those this year. Because of finances, funding issues, that's been delayed, and I don't think it's going to get off until 2026 or 2027, which will be fine if the uh, if the mine agrees with us. So we'll just have to wait and see. Hopefully, we monitor everything. As I mentioned before, this particular formation, this type of material is plastic, and it moves slowly. It actually creeps very slowly, 2 to 5 inches per year generally. When we see it go beyond that, we find that it's moving faster than that. We do remedial efforts to with additional reinforcement in the subsurface. So we're constantly monitoring everything. Actually, we monitor the convergence. How fast is the excavation closing in, back to floor, and rib to rib. With constant monitoring, constantly efforts to maintain safety, and not allow things to get ahead of us. I didn't mention before, we do mine this. We mine with continuous miners in the underground currently. That's probably going to be the standard for quite some time. We're going to be replacing this material. The salt itself is clean salt. I should say it's clean salt, but it's commercial grade salt. You could actually sell it if you chose to, but right now it's not because of what we do here, because we in place for radioactive material in the underground. It's believed nobody would buy this salt if they knew where it was coming from. But the salt is not really exposed to any radiation, so it should be fine for for commercial use. Yeah, good. Yeah, you.
And Mark, I was just curious, can you talk a little bit about the source of the fire, and then also, totally different subject. I heard you were looking seriously into battery electric equipment.
Sure. The source of the fire was a hydraulic leak, actually, one of the lines, and I think one of the continuous miners. I think it was on the continuous miners, or one of the trucks. They tried to actually move that truck before the leak was identified, and before the fire started, they would try to get to an exit point, but they didn't make it, and so actually they ended up having a fire at the worst place you could possibly imagine, and which caused a tremendous amount of smoke to be generated. Fortunately, very fortunately, no lives were lost in that event. It could have gone the other way very easily. I pointed this out numerous times. They just dodged the bullet, and that's how close they came. The radiological release was a product of actually, I guess what happened in one of the facilities, I think it was Los Alamos, they containerize the transuranic waste. They typically use absorbent material, inorganic absorbent material, to absorb any water. Apparently, they ran out of this material and they decided to use kitty litter, which was organic in nature, and didn't react well with the other constituents that were placed in the 55-gallon drum, and basically ended up cracking the drum, which caused the leak to occur. Fortunately, we did have the mag oxide materials that absorb most of the moisture, but the radiological material that was brought into the airflow actually ended up shutting down the mine, because we actually had to we had to containerize that air. That air had to be remediated with HEPA filters to remove the radiological components out of the air. We're in the process of building two large facilities, a much larger building containing much larger which HEPA filters that'll be able to absorb the radiologic material if such release occurs again, and also we'll be able to maintain the airflow in the underground. We also built a salt reduction building to remove any salt out of the air before it goes into the HEPA filters. We don't want to contaminate the HEPA filters with a bunch of salt. So these buildings are actually made for emergency purposes. If there is a radiological release, we weren't able to really address it the last time it happened, because we had to basically shut down the whole mine until we were able in a position to reopen it again. I guess that was one of your questions. What was the other question? I can say. No, as far as batteries, yeah, it's like batteries, as you know, batteries are like, with regard to lithium ion batteries, we're very cautious about this. I guess there's a way to compartmentalize these lithium ion batteries, and I guess that's what's going to be placed in the underground and with equipment and what have you. I'm still a little skittish about this, to be frank with you. I'm not going to lie to you. I'm not happy about this decision, actually, and I'm still very reluctant to have any lithium-ion batteries in our underground. We've used, over the last many decades, we've used diesel-powered, machinery, equipment. There's really no reason why we can't continue to really use that same equipment in the underground. I know people want to get away from utilizing, gas-powered, fossil fuel type of, machinery. But you're still generating all that electricity is generated from probably a fossil fuel source in the first place. Whether you have a battery in the underground that's been charged from a coal-fired power plant a couple hundred miles away, it's kind of really irrelevant. So you're not really achieving anything by switching over to just lithium-ion batteries. It's not really accomplishing what you want to achieve. That's kind of just what my opinion is on it. You can obviously, there's been moves to bring in solar panels into the area so that we can, have electricity being generated on site. You can do a minimal amount of that, but you're not going to generate a heck of a lot of power from those solar power panels. Obviously they're building windmills all over New Mexico right now, and I guess those have a use, but they also have a carbon footprint as well. So you're not really achieving anything really in real terms. With regard to the mine, again, and the use of lithium-ion batteries in the underground, I don't recommend it at this time. Until that technology is improved, I just wouldn't do it. Thank you. Yes.
With the 2.5 inches a year, that width without support, how's that changing?
Well, 2 to 5 inches of creep per year is what we see. That's probably without the support, and then we reinforce, again, with room and pillar design, we use reinforced with rock bolting to constrain that. Now, our rock bolts, they don't hold up indefinitely. We rock bolt, and sometimes those rock bolts fail, and so we replace them. We do additional rock bolting. We actually string the lanyards actually attached to the rock bolts so they don't fall on equipment or people. So we don't want anybody getting injured from when they do snap, the rock bolts snap. We don't want them injuring anyone. So that's what we do to address that. Again, there's certain sections of the mines we can continue to rock bolt. There's other sections that are getting older and we can't just continuously rock bolt. So the yielding arches look like they're a very viable option as far as maintaining the ground. Other questions?
No questions?
Thank you very much.
On behalf of the Service Committee and everybody over here, I'd like to thank you for your very informative presentation. We know trash running waste is a problem because storage is from management, but people like you, we know your expertise is where from the very
Thank you. Thank you very much. All right.
Yeah, and for everybody, next week we have a rather event from Freeport Mandarin, senior engineering session.
All right.
Okay.
Got this.
Took me a little while to get warmed up. Sorry about that.
That's all good. Just keep Take it back in here.
Take this out. Or
Well,
close
it may
this.
crop, yeah.
Close this off.
Close it off before.
There we go. And close this part. Okay. I think
Okay.
that's it.
Thanks, Mark.
Sure, Gil. No worries.
Yeah.
Glad to see you again. Okay.
All right, see you.
Yeah, take care.
Okay. Let's get this
Yeah,
one.
yeah,
sure,
You got to talk to Christine and get this thing replaced.
Yeah, yeah,
Last week we had problems.
yeah. I'm gonna send an email right now, so I'm
Yeah.
tomorrow morning.
All right.
Thank
Your
you, Professor
thing is back.
Vanderlei.
Okay.
Thank you so much.
Thank you very much, Jamal. I
Hey.
appreciate everything he's done,
No
and
problem. Good to
appreciate
see you
your
again.
invitation to have me here.
Absolutely.
And,
Sure.
hopefully, I haven't added to the conversation.
Yep.
Hopefully, we can move forward with other things. I know my colleague's going to be here in 2 weeks, probably talk about similar things. I guess, perhaps.
Yeah.
Like
You
any
mean,
event.
Kurt?
Yeah.
Yeah.
So,
It's fine.
hopefully, it's
We'll
too
try.
not too reductive.